All right, this is the topic 7.4 practice problems on calculating the equilibrium constant. Okay, so this really goes nicely with 7.3, obviously, because we need to be able to write the equilibrium constant equation. Then here we need to use that equation in order to calculate the actual value. Okay, and again, this calculation works for K and for Q, which is the reaction quotient. Again, the only difference between them is that Q is at any point and K is specifically when we're at equilibrium. Okay, so technically there are no equations for this one because the equations came in our last unit. But again, as a reminder, in order for us to calculate these, we're going to have to write them from our balanced chemical equations. All right, so again, paying attention to, are we aqueous, are we gases? If we're gases, we're most likely going to be dealing with pressures. Aqueous, we're going to be dealing with concentrations. And again, if we have a solid or a liquid, that is not included in the equilibrium calculation. All right. So, first one here. All right. Look at our chemical equation. Okay. Is it balanced? Yes. All right. Then we're given these partial pressures. Okay. And we're asked to calculate the reaction quotient. Okay. So what that's telling us is a couple things. One, we're not at equilibrium. Two, these are the specific values. And then three, we're going to be dealing with the QP. All right, so again, in order for us to use these values, we have to write our QP equation. All right, and again, what that is the partial pressures of each of the individuals, right, raised to the power of their coefficient. So the pressure of CO2 raised to the 3 times the pressure of H2O raised to the power of 4 over both of our reactants raised to their respective powers. Okay, so then from there, we just take these values that we know and we plug them in. All right. And if it helps, you don't have to write the units. Okay. Because what's going to happen is that Q and K have no units. All right. So this one here is kind of a nice one for those of us like myself who struggle with unit cancellation. Okay. You don't even have to write them if you don't want to. All right. They will be null. All right. So we just plug this right into our calculator with our exponents and we get out that value. All right. So again, of course, make sure you're watching the we do problems, please and thank you. All right, then down to the you do's. Given the following concentrations for the system, calculate the value for the reaction quotient. So again, right there, that's telling us we're going to be dealing with Q. If we look there, we've got gases, so we're going to be dealing with QP. All right, and if that didn't give it away enough, the units that we're given are atmospheres. Okay. So first off, we got to balance our chemical equation. We got to put a 3 out in front because, again, we have 4 and 2, right? Meaning we're going to have 6 total. So in order for us to get 6 over here, 3 times 2 gives us that 6. All right. So then we need to write the QP equation, the generalized version. So again, each of our products raised to their powers of 1 over both of our reactants, with the first one being raised to the power of 3. All right, then from there, we plug these numbers in, right? 31.1 goes right there, okay? Our 91.2 goes right there, okay? You plug them in, and we get out a final value from our calculator. Again, should be in 3 sig figs because that's the lowest number we have. All right, so again, these are called plug and chug calculators. Plug numbers in, chug them into your calculator. All right, number 2, calculate the reaction quotient for the reaction. Okay, so reaction quotient, meaning Q. All right, we've got solid, aqueous, aqueous. So that means we're going to be dealing with concentrations. And again, that's right there. All right, secondly, solid is a 1. So if we were to write our QC, it would be our our products over our reactant, NaOH. However, NaOH turns to a 1. Right, so this is the concentrations over 1, which again, we usually just don't write. Okay, so then we plug the values that we have in, and our Q value is 27.1. Again, 3 sig figs. Number 3, write the calculations for the reaction quotient for the following system. Okay, if all the partial pressures of the reactants are the same. Okay, and the same for the products. Okay, so number 1 here, balance the chemical equation. We need a 2 and a 2. Okay, number 2, we can ignore this delta H value because it does not play any role in our calculation of the reaction quotient. Number 3, we go over here and we write our QP equation, okay, using our new coefficients, 2, 1, and 2. Then from there, we plug all the values in, being the same at 0.15 atmospheres. Okay, and again, you're welcome to not write the units if you'd like, but at the end of the day, they cancel out and we get 0.15 atmospheres. Okay? Number 4 here, the following reaction is at equilibrium. Okay, so equilibrium is telling us we're going to do K. All right, and it says at a certain temperature. Great, doesn't matter what that is. At that temperature, the value for the equilibrium constant is given. So that's our K value. All right, that is our K value. All right, so K is equal to that number. Then it says if the partial pressure of I2 is 1 atmosphere, find the partial pressure of I. Okay? So this really just turns into an algebra problem. Okay? So if we write our K expression, again, you have to write that before you start. Okay? It's going to be the easiest. All right? We put a 2 out in front of our products because of the 2, and we have 1 there. All right, then we know that this K value is our 3.8, so we're going to replace that. We know that the partial pressure of our reactant I2 is 1 atm. All right, so then this is our variable that we're missing. So what I like to do is turn it into a math equation. That is x raised to the power of 2. Okay, so then I did get a couple questions on how to solve this one in the one below, but basically here, since that's a 1, that doesn't matter. Okay, and how to get the x by itself, you're going to take the square root because we need to undo that squaring. So the square root of this value gets us our 6.16 times 10 to the negative 3. Okay. Number 5 is very similar, okay? The equilibrium constant for this reaction is this, so K is equal to that value. Okay, our lead concentration or our lead ion concentration, okay, so that one is 5.24. What is the concentration of the chloride ion? All right, and again, remember, this one, PbCl2, doesn't matter since it's a solid. Okay, so we rewrite our Q expression, okay, or, apologies, this should be a K, because it says equilibrium constant. Okay, so that should be a K. All right, but at the end of the day here, we're trying to solve for the concentration of chloride. Okay, so we are trying to solve for that one right there. All right, so this turns into a little bit more complex of a problem. So we have 5.8 times 10 to the 4th is equal to this fraction here. Okay, so what you can do in order to get this by itself is we are going to flip our x and our k value. All right. So what you do mathematically is you multiply both sides by x squared, right? And then you divide by 5.88. Okay, divide by 5.88. So what that happens is that cancels with that, and that cancels with that, and we turn this into that expression right there. X squared is equal to that value. Then again, how do we get x by itself? We take the square root. That's our final answer. Okay. Again, if you'd like a little bit more in-depth explanation on how to do the math on either one of these, please let me know. I'm more than willing to sit down with you. Okay? Number 6, given this reaction, A plus B goes to 2C plus D. 2 moles of each reactant were dissolved in 1 liter of water. Okay, so each reactant has a concentration of 2 moles per liter. Okay, so 2 moles per liter. All right. It says at equilibrium, 2 moles per liter of A and B. Okay. All right. Then it says the reaction reached equilibrium. Great. At equilibrium, the concentration of A was 1.64. Okay. So calculate the concentration for each of the substances. All right. So if we went from 2 moles of A and then we ended at 1.6 moles of A, that means we reacted 0.4 moles. Okay? And we reacted 0.4 moles, which means since this is a 1 and this is a 1, B is going to have the same concentration. Okay? Because it's a 1-to-1 ratio. All right? Now on the flip side, we react 0.4 of both of these, and what we're going to do is we're going to form D at the same ratio, that 1 ratio that we lost A and B. Okay, so however, A and B lose 0.4 moles, D gains 0.4 moles. All right, and then finally C, since it's a 2 coefficient, we just multiply that value by 2. And that's how we get our 0.80 moles per liter. Okay. Then the next one, write the equilibrium constant expression. Okay, so since we're dealing with concentrations and we're at equilibrium, it's going to be our Kc. All right, we use our balanced chemical equation, both of our products to their coefficients of 2 and a 1, over both of our reactants to their coefficients of 1. Then the last one here, calculate the value for the equilibrium constant. Okay, so KEQ, all right, EQ meaning at equilibrium. Okay, we use our answers from A, we plug them in, and we solve. Okay, and again, our K value has no units, so it's just 0.10. Okay, also, something I want to point out here, again, this is a really common free response question. So, if you are struggling with A, all right, and you get to C, and you know that you're going to have to use the answer from A in C, okay, obviously it would be best if you could figure it out. But if you can't, make up values, okay? Right up here, A is equal to this, B is equal to this, C is equal to whatever, okay? Then, as long as you use those values correctly in your expression B, you would get the points for C, okay? So again, even if you don't know A, make up fake numbers, right? And then use those fake numbers correctly, and we can propagate that error, all right? So you don't get double dinged. All right, and then finally, the last one here, number 7, this reaction, A plus B goes to 2C, represented by the equilibrium expression there, okay, is equal to 258. Okay, so that's our K value. When 1 molarity of C was allowed to reach equilibrium, and that molarity of A was formed, if this reaction was performed at the same temperature using half of the concentration of C, what would the equilibrium concentration of A be? Okay, so this is a very, very involved problem, okay? But what we can do here is we can turn this into an algebra problem, okay? So our K value there, our K expression there, okay? So, if we look, okay, whatever we decreased C by, okay, whatever we decreased C by was 2 times that which A and B was formed. Okay, why the 2? Because of the balanced chemical equation, all right? And why A minus? Because we're going from 1 mole to 0.5. Okay, so this turns into a very complex algebra problem, all right? You've got x squared, right? Then you distribute and you distribute the square, right? Or multiply, and then you solve, okay? So 7, again, is the most complex version of that problem that I would give you, okay? But very, very low chance, all right? What you need to understand, though, is, again, whatever happens to C happens to A and B, and it happens at the ratio of the coefficients out in front, okay? So on the flip side, if A was doubled, C would be quadrupled, okay? So again, going back to that balanced chemical equation. Of course, if you have any questions, let me know. Otherwise, thanks, guys.